I'm Samantha Zilmer.
My name is Nicholas Alwansky.
I'm Andrew Science.
I'm Alex Zaremba.
And I'm Josh Blumenthal.
And we're Team 53, and we're doing the verification of analog circuits. The goals for the project is to design a small footprint secondary circuit to detect accidental or malicious modifications to a circuit during manufacturing. Another goal is to develop and design and then test the methods of attack to bypass the aforementioned authentication circuit. And the last goal is to use neural networks to help with the authentication of circuits.
Here you can see we've kind of narrowed it down between two different circuit layouts. One of them was the LDO, and that kind of got us started. We used previous research with our mentor, Dr. Kitchen, and then we've kind of we're going to be focusing on this circuit design on the left that shows kind of the dual layout of both the Colpitts and a Hartley oscillator, and we kind of decided to go with those two.
Yeah, so the basic operation of an oscillator is basically just to generate the square wave, and then it can either be voltage or current controlled, but either way it's being fed by a separate system to control the frequency. And then the frequency is totally dependent on the input, which gives lots of vectors of attack.
And then we have a few potential methods of attack that we're going to implement. And the first one we have is like an early failure, which very simply is just to either add or remove components and to see how that affects the lifespan of the product. The next one would be a remote kill circuit, and that would be to modify the PCB traces to create additional or to possibly mess up the feedback loop of the circuit design that we've chosen. And then to kind of tie into that is also with specifically the oscillator is having multiple oscillating modes. So if we somehow change the initial conditions, we could potentially have an alternate mode for the circuit to function in, but it's not the one that it was intended to be in, and would also cause it to break down and deteriorate faster than it was intended to.
In order to verify the circuit and detect Trojans within it, there's three options that we're considering. We first have frequency domain analysis, which means we would inject noise into the circuit, and then we would look at the transfer function of the frequency domain and compare it to the transfer function of the golden circuit when we simulate it. And then if we vary the input voltages and compare the transfer functions at each voltage in our golden circuit, then we'd be able to detect different Trojans within the circuit. And then the second option is we have a circuit operation with different inputs. So we feed an input some sort of waveform, and we see what kind of waveform comes out in the output. And lastly, we're considering neural networks, possibly using Python or MATLAB in order to find all the different categories within the output as far as frequency, amplitude, and such for our golden circuit. And then by using that, we can train the neural network off of our perfect circuit, and then we can see any sort of differences between our produced circuit that may have been hacked, so we can detect Trojans that way.
The purpose of a neural net is basically it's modeled off of the neurons in the brain of like the humans or animals. And what we're going to use this for is a machine learning, because machine learning is a machine that learns through experience. So our plan is possibly to create a data set of working voltage control oscillators and be able to train the data set and use machine learning to test new circuits. And that is the end of our presentation.
Thank you.